So today we'll discuss assignment related to bonding structures and shapes. In the last session, we completed first 20 questions, and today we'll discuss 20 onward. So in the first question, question 21, the lattice energies can be measured by using a Born-Haber cycle or can be calculated by electrostatic theory. In electrostatic theory, we considered ions are perfect spheres. The lattice energy of a magnesium chloride and magnesium iodide are shown. So the lattice energy from Born-Haber cycle using the experimental lattice and the lattice energy using the electrostatic theory. What does this data indicate about the bonding in magnesium chloride? So bonding in magnesium chloride, it is minus 2500. Negative sign shows that it is an exothermic. So it is minus 2526 and then minus 2200 and minus 2326. So there's a difference between experimental and the electrostatic. So what it shows that ions are not perfect sphere. If ions were like perfect spheres, then the theoretical lattice energy should matches with experimental lattice energy. So what it indicates, the difference between the theoretical and the Born-Haber experimental value, it shows that ions are not perfect sphere, or we can also say that bonding is not 100%. The bonding in magnesium chloride MgCl2 is not 100% ionic. Because of distortion, there is a covalent character. So basically what happened, like if this is a magnesium ion and then the chloride ion, so chlorine ion distorted or polarized due to magnesium. So that's why we find the difference in the theoretical and the experimental value of the lattice energy. Is it clear? The next part explain why there is a greater difference between the experimental Born-Haber and theoretical lattice energies for magnesium iodide compared to that of magnesium chloride. So when we compare magnesium chloride, we find a small difference. You can see it's about 200. About 200. When you check a difference, it's about 400 between the theoretical and the experimental. So why there is a greater difference in magnesium iodide compared to that of magnesium chloride? Basically what happened in magnesium chloride, chloride ion is smaller in size, so there will be a distortion, but there will be smaller distortion, less polarization. But iodide ion is larger in size, so as it is larger in size, what happened? The distortion of iodide ion will be greater. So how we write this answer? So what is the reason why there is a difference? First thing you should mention, iodide ion is larger than chloride ion. So easily distorted. You can say easily distort, or you can use the word polarized. The distortion of the ion depends on the size of a positive ion, it should be small, charge of the positive ion, it should be big, and the size of the negative ion should also be larger. In question 22, draw a dot and cross diagram to show electronic structure of compound magnesium chloride. Only outer shell electrons include the charges to represent. So dot and cross, magnesium belongs to group 2, so it will lose all of its valence shell electron, and chlorine belongs to group 7, and we just have to draw the outer shell electron. So magnesium electronic configuration is 2, 8 and 2. So once it lost these 2 electrons, there are no outer shell electron in that third shell. The second shell will be outer now, so it will have 8 electrons. And with a charge plus 2, chlorine belongs to group 7, so it is already having 7 electrons in the outermost shell. One it took from magnesium, so this chloride ion will have a negative charge, -1. And same way, another chloride ion also took one more electron, so this will also have negative charge. Then draw a dot and cross diagram to show electronic structure of compound tetrachloromethane. So tetrachloromethane, it's a covalent compound. So how we can represent or draw the structure of tetrachloromethane? So there are 4 chlorine, and meth means 1 carbon will be there, so this will be 1 carbon, and 4 chlorines will be. It's a dot and cross, so bond angles are not important. If you represent cross to represent carbon at electrons, then dot will be there to represent chlorine. And then these are the lone pairs. So 3 lone pairs are there present on the chlorine. The next part suggests why the melting temperature of a magnesium oxide is higher than magnesium chloride, even though both are almost 100% ionic. So what is the reason? And it's of 3 marks. So why magnesium oxide is having the higher melting temperature? Both are solid, magnesium oxide and magnesium chloride, but magnesium oxide is having a higher boiling temperature as compared to a higher melting temperature as compared to magnesium chloride. So when we compare oxygen, you can see in magnesium oxide, oxygen charge is -2, compared to chlorine charge, which is -1. So the effect of a greater charge, so there will be a stronger force attraction in magnesium oxide compared to magnesium chloride. And then you will compare the size. Oxide ion is smaller in size compared to chloride ion, which increase the attraction between the ions. So when ions are closer, They have a stronger attraction, that's why. So these are the points you should include. So compare why magnesium oxide, like if you were having a magnesium oxide, it will have a higher melting temperature as compared to magnesium chloride. In question 23, a molecule is, what is a molecule? A group of atom bonded ionic. So that's a group of atom bonded covalent, because we have covalent molecules. For ionic, we say it's a lattice and the regular arrangement is there. A group of ions, there are no ions in a covalent bonds, and group of atoms bonded by metallic, that's also a wrong. So basically, a molecule is a group of atoms bonded by covalent bonds. In question 24, which of the graph shows from left to right the trend of ionic radius? So these all are isoelectronic. How they're isoelectronic? Because oxygen, nitrogen, there are 7 protons and 10 electrons. Oxygen, there are 8 protons and 10 electrons. Fluorine, there are 9 protons and 10 electrons. Sodium, there are 11 protons and 10 electrons. Magnesium, there are 12 protons and 10 electrons. And aluminum, there are 13 protons and charge is there, so 10 electrons. So all of them have the same number of electrons. So aluminum size should be much smaller as compared to any other in this series, because the force of attraction, as 13 protons are attracting 10 electrons, so there will be a stronger attraction. So aluminum should be the smallest size. So when you check, you can simply identify, like this is aluminum, 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 and aluminum. So this aluminum is having the smallest size, so that's why A is the right answer for this question. Is it clear? Any doubt in this part? Moving on to the next question. The ionic radii in nanometer is shown for lithium, fluorine, calcium. Which of the following compound has the most exothermic lattice energy? Like which will have the highest lattice energy? So to have the highest lattice energy, their charge should be big and the size should be small. So when we compare the charge should be big. Lithium fluoride, so plus 1 minus 1, lithium chloride plus 1 minus 1, calcium oxide plus 2 minus 2, and plus 2 minus 2. So it shows that either calcium oxide will be there or calcium sulfide. And the size should be small. So when we, calcium is the same when we compare oxygen, with sulfur, so oxygen is smaller in size, that's why C is the right answer for 25A. Is it clear? Because the lattice energy required to convert these ions in a gaseous state, or energy released basically when ions in the gaseous state form a compound, and it is exothermic. So Higher exothermic when ions are smaller in size and they have a greater charge. Which of the following compound shows the greatest difference between the experimental? So for experimental difference, the size of positive ion should be smaller and the size of a negative ion should be greater and the charge of a positive ion should be greater. So when we compare calcium sulfide, calcium is plus 2, sulfur is minus 2. And so its size should be larger, so it will have a greater distortion. That's why D will be the right answer for the second part. In question 26, a briefly describe an experiment with a diagram of operators you could use to show that there are oppositely charged ion in copper 2 chromate. Copper ion is blue in color and chromate ion is yellow in color. So what we can do to show this, so we can use electrolysis. So for this electrolysis, we can set up electrolytic cell like two containers connected by a salt bridge, and then electrodes are there. One is connected with a positive terminal and the other one is connected with a negative terminal. And we can have the solution of copper 2 chromate. So when we do electrolysis, the copper ions are positive, so they will move towards negative. So this solution will turn blue. And chromate ions, as I mentioned, they are yellow in color, so they will move, and they are negative, so they will move towards positive. So this side of a solution will turn yellow. The part B, the ions in ionic lattice are held together overall by force of attraction. Describe the force of attraction in ionic lattice. So, force of attraction in an ionic lattice, that force is between the oppositely charged ion, or force is their electrostatic force between the positive and negative ions. So that is the force, and the description for the experiment, the experimental part, that we will see the blue colors, blue ions will, or yellow ions will move towards the positive electrode and blue ions will move towards the negative electrode. And here electrostatic force between the opposite charges, and two forces of repulsion that exist, so between the positive charges and between the negative charges. These are the forces which exist. In question 27, metals are good conductor of electricity because, so why the metals can conduct electricity, or why they are good conductor of electricity? So when we check the statements, metal atoms are arranged, not metal atoms, there are metal ions, so it cannot be A. Metal ions are very close to each other. Yes, they are very close, but that's not the reason for conduction of electricity. Metal ions are not free to move. Electrons are free to move. Electrons are free to move through the lattice. That's why the metals are good conductor of electricity. In question 28, which of the following statements is evidence for existence of ions in an ionic compound? Ionic compound. So which one explain the ionic compound evidence? Ionic compounds in solid state conduct electricity. That's wrong. When any ionic compound is in solution is electrolyzed, migration of ion can be seen. We can, because some of the ions are not, or not all of the ions are colored, so we cannot see all of them. Some ions, yes, we can see, but not for all the ions. In electron density map, ionic compound, there is no single line represent the electron density of both cation. So that's right, because when we use an electron density map, we use separate lines to show these electron density map. Like when we are representing, if I say sodium chloride, so electron density map, the lines of sodium ion and the lines of chloride ion will be separated from each other. So they will not combine with each other, they are actually separated from each other. So C is the right answer. If they ask for covalent, then electron density map for ionic are some single lines represent. So that is, D statement is actually representing not ionic compound, it is representing covalent compounds. Question 29, white phosphorus consists of. So what white phosphorus consists of? It is a simple molecular structure. It's not a giant atom or giant ions. It is actually a small molecule. In question 30, this question is about lithium iodide and ionic salt. Draw a dot and cross diagram to show lithium and iodide ions. So lithium will have, because lithium is, the electronic configuration is 2 and 1. So it will lose the last cell electron, so it will be +1. And the chloride ion took one of the electron. It belongs to group 7. So 7 are already there and one it take from lithium, so it will form a chloride ion. In part B, the experimental lattice energy of lithium iodide is 759 and theoretical energy is different from this value. Will the experimental lattice energy more negative or less? So experimental lattice energy is always more negative. Why? Because ions, in a theoretical we consider ions are perfect sphere, but practically what happened, experimentally what happened, ions are not perfect sphere, so the distortion is there, and due to the distortion the ions are closer to each other. That's why the experimental lattice energy is always higher than the theoretical lattice energy. So the experimental lattice energy will be higher. More exothermic, and that is due to the distortion or polarization of iodide ion. Ions are closer, which required so strong force or more energy is released. Is it clear that why the theoretical lattice energy and the experimental lattice energies are having a difference, and why experimental is higher than theoretical? Is it clear, this part? Then state and explain how electron affinity means when electron is added to a neutral gaseous atom, we call that as electron affinity. value changes as we go down from chlorine to iodine. So when we go down from chlorine to iodine, the size is first is a chloride ion, then first chlorine, bromine, and iodine. So when they gain an electron, they release energy. So you have to state the order, like what is the trend in this electron affinity as we go down the group. So as we go down the group, it becomes less negative for this group 7. So electron affinity become less negative, moving down the group. And what is the reason? As electron is added further from the nucleus, or we can say more shielding effect. So when greater shielding effect is there, energy release will be, because there are more electrons in case of iodine as compared to that of bromine, and bromine more electrons are there as compared to that of chlorine. So as there is a greater shielding effect, this electron experience less repulsion, easily added, so less energy release. But here, when this electron added, there is more repulsion, because less shielding effect, more repulsion. As we go down the electron, this electron affinity decreases or become less exothermic. Is it clear? In question 31, the lattice energies can be calculated from electrostatic theory, the theoretical as well as Born-Haber. What can you deduce from the fact that experimental and theoretical lattice energies of barium chloride are very close? So when lattice energies are very close, it means the bonds are 100% ionic and there is no distortion. So bonding is 100 or almost 100% ionic and there is no polarization or distortion. So when we have experimental and theoretical lattice energies are similar or close to each other, it shows bonding is 100% ionic and there is no distortion or polarization to the ions. Next is 32. Which of the following result is most polarization of the cation? So negative ion, most polarization. So size of the cation. So cations move towards cathode. They are positive ion basically. So size of the positive ion should be smaller, and so size should be very small and the charge should be larger. So that's why B will be the right answer. That because a smaller positive ion with a greater charge will cause more distortion to the negative ion. In question 33, which of the following has the smallest radius? So how you can work out the radius? You will check comparison should be there between the number of proton and electrons. So when you check So fluorine, there are 9 protons, 10 electrons. 12 protons, 10 electrons. 11 protons, 10 electrons. And 8 protons, 10 electrons. So smallest, so one which is having more protons than electron, greater difference. So B will be the right answer. Which of the following contain a dative bond? So dative bond is there in ammonium. Nitrogen belongs to group 5, so it will share 3 electrons. And there is a lone pair on nitrogen, and that lone pair is shared with one of the proton or hydrogen ion. So that's this bond is a dative one. So B is the right answer for this. For question 35, potassium combined with iodine to form potassium iodide. Which of the following describe the bonding in 3 substances? Potassium is a metal, and metals will have metallic bond. Iodine is a non-metal, and non-metal will have covalent bond. And potassium iodide is a metal and non-metal. When metal and non-metal combine together, they will have ionic bond. So which one, all the results are correct? So that matches with option D. In question 36, ions with the same electronic configuration are said to be isoelectronic. Which of the compound is made from isoelectronic, like have the same number of electrons? So calcium oxide, how calcium oxide is formed? By calcium ion and oxide ion. So calcium is having 20 electrons, but calcium ion will have 18 electrons. And oxygen is having 8 electrons. It will have minus, because ion will have 10 electrons as it take 2. In calcium bromide, and when we check sodium oxide, so sodium is having, in sodium oxide there will be a sodium ion and oxide ion. Sodium is having 11 electrons, but if plus 1 means it will have 10 electrons. And oxygen is having 8 electrons, minus 2 means it will have 10 electrons. So both the ions have the same number of electrons, that's why we call them as isoelectronic. Is it clear? Question 36. Each diagram shows a trend in ionic radius for 4 sequence of ions. The diagram is not to scale. So we have to select which diagram shows a trend of ionic radius, sodium, lithium. So down the group. So down the group the size increases. So as the size increases, which of them is showing increase in size? So A is showing increase. A is a graph which is showing increase in size. So for first one, A is the right answer. The second part, which diagram shows a trend in ionic radius for sodium, magnesium, aluminum, and silicon? So across the period, the ionic radii decreases. Why across the period the ionic radii decreases? Because more charge or greater charge density is there. That's why the value for ionic radii, as we go down, as we move across the period, it decreases. So D will be the right answer. That graph D, which shows a decrease. Question 38. Some energy changes are involved. Electron affinity. Electron affinity means when electron is added. To neutral gaseous atom. Lattice energy means when ions combine, ions in the gaseous state combine to form a compound. Standard atomization means when we produce 1 mole of atom in a gaseous state. And formation means when element form the compound. That's called formation. So which enthalpy change or energy change represented by P? So you're producing an atom in a gaseous state. So when you produce atom in a gaseous state, what we call We call that as atomization. So C is the right answer. Then elements are forming a compound. When elements are forming a compound, we call that as formation. So D will be the right answer. And again, in the last one, enthalpy change or energy change, when molecule form an atom in a gaseous state, so that is also atomization. So again, C will be the answer. So this is atomization. Why? Because you produce 1 mole of an atom. This one was formation. Why? Because the element forms a compound. Question 39. Which row in the table shows the lattice energy in kilojoule for calcium fluoride, potassium fluoride, and potassium iodide? So first thing, calcium fluoride should have the highest value. Why? Because calcium ion is having a greater charge and fluorine is smaller in size. So it will be closer to calcium, which should have the highest value. Then followed by potassium fluoride, because we are talking about lattice energy. So potassium fluoride charge is +1 on potassium and fluorine -1, and ions are closer. And for potassium chloride, potassium iodide, because the charge is same, but the size are larger, so lattice energy will be smaller. So potassium iodide should be small, and calcium fluoride should have been the highest. So highest number -2000, and the smallest is 651, and the moderate is 817. Is it clear? The lattice energy means when ions in a gaseous state will form a compound and release energy. It's always exothermic, so that's why it is negative. And question 40, the experimental value of the lattice energy of beryllium iodide is -2800, whereas theoretical is -2600. So there's a difference. Why there's a difference in the theoretical and the experimental lattice energy? Because there's a distortion. And how the distortion effect? Beryllium ion is smaller in size, so it will cause, or the distortion is there for a negative. Size of the positive ion should be smaller, size of the negative ion should be larger to cause a greater distortion. So beryllium ion is smaller in size and it polarizes the, because why options C and D are wrong? They mention polarizes the beryllium ion. Positive ion cannot be polarized, negative ion can be polarized. So iodide ion will be polarized, and why it is polarized? Because of beryllium. So B will be the right answer for this question. So this was assignment related to bonding, structure, and shapes of the molecule. Any question related to the class today? Any question or a doubt? So I'll end the session and share this.